Welcome back, folks. Today we're going to talk about specific heat, but in order to talk about specific heat, we need to first talk about types of energy and the energy flow. So this is something that we've kind of discussed in the past, but we're kind of revisiting it here now with a little bit of more knowledge than we had before. So temperature, as we said before, is the measurement of the kinetic energy in an object. When an object changes physical states, meaning when it goes from a solid to a liquid or a liquid to a gas, this energy absorbed or released in this form is called potential energy. Now, energy, whether it's kinetic or potential, is measured in something that we call joules, which is a unit that we have seen in the past. Now, what's interesting about energy in general is that key point there at letter B. It says that energy evolved in phase changing is potential energy. And this is actually something that we've discussed in the past, that if you measure the temperature of something when it's going through a phase change, you will notice that the temperature stays consistent. Say, for example, if you took a thermometer and put a thermometer in boiling water, you would notice that the temperature of that water hits a certain point and then never changes again. This is because all of the energy involved in phase change is potential energy and is not measured by temperature. Temperature is a measurement of kinetic energy. Now, energy transfers in two different directions. We've talked about this a lot. Endothermic changes is where energy is absorbed from the surroundings. Go ahead and add that to your notes there. Energy absorbed from the surroundings. There we go, from the surroundings. So again, endothermic changes is when energy is absorbed from the surroundings, where exothermic changes are when energy is released into the surroundings. Okay, so probably not from the surroundings, but into the surroundings. Okay, so let's keep going. So now that we got it, let's talk about specific heat. So remember that specific heat is the amount of energy required, or I don't know if that should be required. Hold on, I think that might be a typo there. Let me see. Oh no, yeah, required or released. So I don't know why it says cha-cha change, but it's the amount of energy required if we're talking about something that's endothermic, or released if we're talking about something that's exothermic, to change, again, I don't know why it says cha change, to change the temperature of 1 gram of a substance 1 degree Celsius. Okay, so we've talked about specific heat in the past, and if you remember, the equation that we use for specific heat is the Q equals mc delta T equation, where m is mass, c is specific heat, Q is heat, and delta T is the change in temperature, which sometimes we can relate to as delta T equals Tf minus Ti. We only use that when we have to look for one or the other, otherwise we can just use delta T. When a substance undergoes a rise or fall in temperature and remains the same state, the specific heat may be used to calculate the amount of energy involved. I don't know why I wrote the formula in the section for the units. Let's slide that down. Sorry for all of you writing in pen. The units for specific heat are, let's see, so C is our value for specific heat, and it is in joules over grams degrees Celsius. Grams times degrees Celsius. So there we go. Now we are all good. So again, this is the amount of energy required to change the temperature of a substance if it's not going into a phase change. So remember that when something is going through a phase change, technically its temperature is not increasing or decreasing. So this is only when we are in the same state. As soon as we go like from a liquid into a gas, that requires something different, which we'll talk about more later. Okay, let's see. So if you recall, we had a value for the specific heat of water that we use pretty much consistently. I believe in the past we used 4.184. 4.18 is also fine. It just depends on what you want to do. There's a lot of different specific heats. Depends on the substance. Most of the time the specific heat is given to you if it's not dealing with water. Sometimes specific heat is the thing that we're looking for, but they are values that you won't have to memorize. I would know the one for water though, but they're not anything you ever have to memorize. You're either given it or you are looking for it. So let's look at some examples. Let's do a little practice. Let's calculate the quantity of heat in kilojoules needed to warm water from 25 degrees Celsius to 95 degrees Celsius. The cup holds 125 milliliters of water. So it gives us water in milliliters, but we need grams for the equation, right? Because we're looking for Q equals mc delta T. And in this situation, we are looking for Q. That's the quantity of heat in kilojoules. Remember that the equation spits out joules. So we want to make sure that whatever we get in joules, we then convert into kilojoules. Don't forget that we can quickly convert our milliliters of water into grams of water thanks to the density of water. Because water's density is a 1-to-1, we can just convert it. So now we have everything we need. Let's go ahead and set it up and knock it down. So we have 125 grams. We have the specific heat of water, which is 4.184 joules times grams degrees Celsius. And in this situation, technically, we're going to get a negative number for TF minus TI. But since we're not looking for either one, why don't we just keep it positive? Why don't we just do 95 minus 25? Oh, forgot my units on the 95 there. We're going to make sure that we stay to our sig figs here. This is a problem that requires two different types of sig fig rules. When we subtract 95 and 25, we're going to get 70 degrees. 70.0, which is 3 sig figs when we start multiplying. So that means our answer we get is about 360,000 or something like that. But we want to convert that into 36.6 kilojoules. The reason why I just answered it in kilojoules when I first did it, so I don't remember what it is in joules. You move the decimal over a couple times. Either way, you get kilojoules. Okay? That's all it takes. Plug it in, solve for what you need. All right, let's go ahead and look at the next one. It says how much energy is required to heat an iron nail. And it gives us a specific heat. And it says that it has a mass of, I don't know why there's not a blank there. My notes on this particular section have been all goofed up. It should be 14 grams from 25 degrees Celsius until it becomes red hot at 750 degrees Celsius. So this is just another thing where we're plugging in, solving for Q. Why don't you go ahead and give it a pause and try it out. Come on back when you're done. Okay, so if you plug everything in that's given, you should get something like this. You get an answer that's about 4,500 joules, or if we round that up to kilojoules, that should be 4.5 kilojoules. Now, what if we're trying to solve for something else? Let's see that we have something that's 5,570 joules of energy are added to 400 grams of lead, which has a specific heat of 0.13 at 24 degrees Celsius. This time we're looking for TF. So we have to open up that delta T equation and solve specifically for TF. You got two choices here. You can either solve the entire equation for just delta T and then use delta T to get to TF, or you can open up the entire thing and solve just for TF. Go ahead and pause and come on back when you're done. Regardless of the method that you chose, this should be the answer that you got, 134.6 degrees Celsius. For this last one here, I want to do this one together, so don't worry too much about it. We will work on this one in class. That's all for specific heat, folks. We've seen specific heat in the past already, so hopefully that wasn't too painful. We'll see you next time.